Let's take a minute to touch base about formal charges and Lewis structures. In this video, we're going to go through the structure for the thiocyanate ion, or SCN-. So if we have SCN-, this means we have a total of 16 valence electrons. If we write out the skeleton structure, we'll put carbon in the center because it has the highest bonding capacity, but also because it is the least electronegative atom. As we go through, we draw our atoms, we make our single bonds between them to make a skeleton structure. Then we add on the valence electrons to the outer atoms to complete the outer atoms' valence electrons. If we do a quick accounting of the valence electrons in the structure, we have a total of 16 electrons. Sweet! But we're not there yet. What's wrong with this structure? Well, none of our atoms are acting in accordance with their bonding capacity, but most importantly, carbon does not have a complete octet. In this instance, how do we give carbon a full octet whilst preserving our 16 valence electrons? We make double bonds between the outer atoms and carbon. Now we have a few possibilities here. This is where resonance structures come into play and why it's so important for us to calculate the formal charge to determine which structure is the favored one and contributes the most to the resonance structure. Because we remember that if we have the ability to make a resonance structure or pass bonds between the atom, then the actual structure is a mixture of the three where one structure may or may not contribute more than the others. So our first option is to make another bond between carbon and nitrogen and carbon and sulfur. So making two double bonds, one on each side of carbon. All atoms have 8 valence electrons, and carbon and sulfur are both at their bonding capacity, so they're making the number of bonds that they should be making, which means they have a formal charge of 0. Nitrogen, however, is making one less bond than its bonding capacity dictates. Another option is to make a triple bond between nitrogen and carbon, so both nitrogen and carbon are obeying their bond capacities. However, this leaves sulfur short of one bond than it should be making based on its bond capacity. The final option is one where nobody except the carbon is happy. The carbon is forming a triple bond with sulfur and a single bond with nitrogen. Sulfur has exceeded its bonding capacity, while nitrogen is short of its bonding capacity. Intuitively, we can probably figure out that the one where neither substituent atom makes its bonding capacity is not the best structure. But how can we determine rationally which of the other two structures to choose? The answer comes down to formal charge. Let's go through and calculate the formal charge for each atom in each of the molecules. Remember, we are calculating the formal charges of each atom individually. When we add the formal charges of each atom together, they should equal the charge of the whole molecule. So, for SCN-, we want all the formal charges of the atoms in the molecule to add up to -1. Let's do it. Another way we can think of calculating the formal charge is it's the electrons an atom should have minus the electrons it does have. So now that we've calculated the formal charges for each molecule, let's make sure the charges add up to -1 for each. And they do. Now let's walk through each molecule and use the rules from our outline and book to ascertain which structure is the best. Now, we went over that the best structure, or the one that will contribute most to the actual structure, is the one where the formal charge is 0 on every atom. Nope, none of these molecules satisfy that criterion. So let's move on and figure out what the best contributor is with our next set of parameters on the list. So if we don't have a molecule where all of the formal charges are equal to 0, then the next criterion is that the number of formal charges on the molecule should be minimal, so you want the least number of charges possible, and we want those charges that are on the molecule to be as small a magnitude as possible. This rules out the structure on the right. Why? First of all, we have charges on 2 atoms as opposed to 1, like the structures on the left, and nitrogen has a -2 charge in that structure. So we rule out the right-hand structure for having too many and too large charges. That brings us the left-hand 2 structures. If we have 2 molecules with the same number and size of the charges, which both of these molecules have one -1 charge, it comes down to whether or not the charges rest on the best atom. So a positive formal charge would want to be on the least electronegative atom, while the negative charges should be on the more electronegative atom. Let's look. If we were to look at our electronegativity table, we would see that nitrogen is more electronegative than sulfur. Why? Even though sulfur is further on the right on its period than nitrogen, and therefore would have a larger Z effective, the addition of another N level matters here. That extra N level dampens the pull of the nucleus more than an added proton would increase it. So if we're stuck between 2 structures, one where the negative charge is on the sulfur and the other where the negative charge is on the nitrogen, the structure where the negative charge on nitrogen is going to win. Why? Because nitrogen is more electronegative. Therefore, if we're going to pick the best structure out of a resonance structure set, or the one that contributes the most to the actual structure, because remember, resonance structures are a weighted average or a blending of all the possible structures, it's going to be the one in the middle, because the middle structure has the minimum number of charges, the charges are small in magnitude, and the negative charge is positioned on the most electronegative element. Remember, when a molecule has resonance structures, the actual structure, again, is a blending of the possibilities. When we calculate the formal charges for the atoms within a molecule, this can help us determine which structure is the biggest contribution to the actual structure, or which structure the actual structure looks the most like. Let's take a chance to look at another molecule, carbonate, or CO3₂-. We have a total of 24 electrons. We draw out the skeleton structure and then add electrons to complete the octets of our oxygens. Now, if we count the electrons, 8, 16, 24, we have the right number. But what's wrong here? Carbon doesn't have a complete octet. What do we do when we have the right number of electrons, but our central atom, carbon, doesn't have a complete octet? We take a lone pair from one of the oxygens and turn it into a double bond between the carbon and the oxygen. Therefore, both the oxygen and one of the carbons will have an octet. It's just one set of one of those electrons is shared between 2 atoms. Is this the only structure that carbonate can occupy? If you're thinking no, then you're right. Carbon can form a double bond with each of the oxygen atoms for a total of 3 different structures. Now, we're not done with our Lewis structures until we write down the formal charge of each atom next to that atom. We can see here that there are 3 different resonance structures. However, the formal charges are the same for each structure. In each, the carbon and 1 oxygen have a 0 charge, while the other 2 oxygens with a single bond have a -1 charge. Note, if you see an oxygen with a single bond and 3 electron lone pairs, you can assume that it's a negative charge, and you'll begin to see the patterns as you work on Lewis structures. So if we have 3 equivalent structures where we're passing a double bond between an equivalent atom, we have the same formal charges on each molecule. This begs the question, which of these structures is favored? Which of them contributes the most to the actual structure of carbonate? Well, none of them. With the resonance structure for CO3₂- or carbonate, we have 3 equivalent structures. Since they're the same in terms of bond distribution and formal charges, no structure is favored. Rather, the two structure is an average of the three different structures. In fact, the true structure is actually something like this. The result of having equivalent resonance structures is that each carbon-oxygen bond isn't really a single or a double bond at any given point in time. It's more like having a 1 1/3 bond all the way around. Carbon still maintains its octet because it has 3 1 1/3 bonds, which gives you a total of 4 bonds. So what's the deal with picking the major contributor to a resonance structure based off formal charge? Sometimes there will be a winner that you can determine based on formal charges. If there is one, you'll need to be able to draw and identify the structure that is the major contributor to the true structure of the molecule. If there isn't a winner and all of the structures are equivalent, like carbonate, you'll need to say that there isn't a major contributor. In fact, in all cases, it's important to understand the results of blending these equivalent structures results in a true structure, and when you have equivalent, and that the bonds are not single or double bonds, but in this case, especially in the case of carbonate, the resulting structure has a partial double bond character rather than being a single or a double bond at any given point in time.